In section 6.5, we are going to learn how to find the length of a curve. And more specifically for right now, we're going to be given a function and an interval to find the length for. So we might have the function f of x on the interval from a to b, and we're being asked to find the length of this piece of the curve from a to b. So this is not a straight line. We can't just use our algebra distance formula because the algebra distance formula, like I just said, assumes it's going to be a straight line. And a straight line has a constant slope. Which means there's no change in the slope. If there's no change, then we can use algebra. But when there is a change going on in the slopes, we need to use calculus. Remember, calculus is the mathematics of change. So here we have our curve. It's got changing slopes. And we must use calculus. With that constant slope, we can use algebra. But I'm going to show you a little proof. Now, you do not have to know this proof. I'm never going to ask you to recreate this proof, but I think it's kind of interesting. It shows you how we can go from the algebra slope or algebra distance formula to the formula we're going to use in calculus. So we're talking about these slopes changing, and that's why we have to use calculus. And you are going to see part of this formula is going to have slopes in it. And remember back to calculus 1, what we used to find slopes on a curve, tangent slopes, was derivative. So we will see derivative in this formula. We call this, when we find the length of that curve, we actually call it an arc. We call a piece of a function an arc. So what we're actually finding here is arc length. And in other calculus textbooks, I've actually seen this section called arc length. You may have heard the term arc length before. We use it in trigonometry to find distance along an edge of a circle, which is still appropriate because the edge of a circle is not a straight line. We can't use the distance formula. We use another method. But because the curve on a circle is predictable, we end up using another formula for it that involves some trigonometry. But these curves on our functions are unpredictable. We're going to come up with a general formula that we can use on any function here in calculus. So I'm going to show you the proof. Again, you do not have to know this proof. I'm not ever going to ask you to recreate this proof, but it's kind of neat to see. So if we know that we want the distance from x1, y1 to x2, y2. And this is just the straight line distance formula in algebra. So we would say d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Now I'm going to do some fancy manipulation on this for just a regular old person seeing something like this for the first time, some of the things I'm going to do, you would never have thought of in a million years to do that. And that's perfectly fine. So the first thing I'm going to do, and we can do pretty much anything we want as long as it is mathematically legal. We don't break any math rules. Everything inside is going to be left alone on this first step. But what I'm going to do is I'm going to multiply by a fraction that technically has a value of 1. And it is the square root of x2 minus x1 squared over the square root of x2 minus x1 squared. We've got the exact same expression in the top and the bottom, so it has a value of 1. Now I'm going to take the one that's in the denominator, and because it's under a square root, I'm going to go ahead and combine it with the stuff in the first square root. Both of those expressions are under square roots, so I can really put them all together under one square root. And my first square root has 2 terms under it, so I actually have to distribute it to both of them. And that one's in the denominator, so when I distribute it, it's actually going to be divided. And this turns into x2 minus x1 squared over x2 minus x1 squared plus y2 minus y1 squared over x2 minus x1 squared. And we still have this one on the outside. And we can do some algebra simplification. This first piece is just equal to 1. Now this piece, there's actually a different way that we could write that. And I'm going to jump several steps here. So first, y2 minus y1 over x2 minus x1. That may look kind of familiar, and it's something that we learn in algebra class. That's actually the slope formula in algebra. The slope on a straight line if you know 2 points on the straight line. Well, we're trying to change this algebra formula into calculus. So in calculus, we don't use points to find slope. We use derivative to find slope. So we're actually going to replace this with derivative, because we don't want just the straight line slope between 2 points. I want to be able to find the slope at lots of little points individually along the way. Now, I haven't done anything with the squared, so I'm going to leave the squared on it. On the second piece, the square and the last piece, I guess it is the second piece. The square and the square root cancel each other out. x2 minus x1, that just represents a change in the x value, which we could also write as dx. And typically we see that dx at the end of an integral. And I'm going to go back to my picture, and I'll actually write it, I'll draw it again here underneath our formula. This is actually our formula for finding arc length along f of x on the interval a to b. And what this is doing for us it is finding straight line distances, because that's the formula we used. But what it's doing is, because we have this x2 minus x1, this dx, delta x always represents a very, very, very small distance in the x direction. So what this is doing is it's actually breaking down our interval a to b in tiny, tiny, tiny little subintervals. And this little subinterval is our delta x. And then it will do another one. and then it will do another one, and then it will do another one. And if you zoom in, and I'm going to try to zoom in here, let's see. I don't know if I'll be able to. If you zoom in to any one of these subintervals and just look at them individually, they look like straight lines. So each of these subintervals could use the straight line distance formula. As long as we use each individual subinterval's slope and length. So that's why we're using f prime of x for that specific subinterval, and we need the length of that subinterval, which is the dx. And we want to do this for all those tiny little subintervals from a to b. So it does originate from our algebra distance formula, but we just kind of tweak it a little bit. We're breaking it up into lots of little pieces and using individual slopes for those subintervals. So that's why the f prime of x is put in there and the dx is put in there. So I will write this one more time. Arc length we use the letter s to represent arc length, is the integral from a to b of the square root of 1 plus f prime of x squared dx. And this is for the function f of x on the interval a to b. So let's look at a couple of examples. We're going to find the arc length on the function f of x equals x squared minus 2 on the interval -1 to 3. You don't necessarily have to draw this problem in order to be able to do it, but just to get an idea of what we are doing, I'm going to go ahead and draw it. So x squared minus 2 is just a parabola with its vertex at 0, 2. It also goes through the points -1, -1, and then 1, -1, 2, 2, and then 3, 7. So I'm just drawing the piece that we need. And I missed most of my points, but you get the idea. We want to know how long this curve is, or this arc is. There's -1, and there is 3. So obviously we can't just do the straight line distance from -1 to -1, from -1 to 3, 7. That would be this distance, and obviously that distance is much shorter. If you remember the saying, the shortest distance between 2 points is a straight line, that's always going to be true. You could check that distance real quick to kind of verify that the arc length that you found is reasonable and fairly accurate, because your arc length should always be longer. Sometimes there's not a lot of difference, and if you draw them, you can see that there's not much difference. Sometimes there's a huge amount of difference, and obviously your picture would give you an idea if they should be close values or if they're going to be very different values. So if you remember from our formula, we actually need f prime squared under that square root. So for the function we were given, f prime is going to be 2x, and then if we square that, f prime squared is 2x squared. Be careful when you square that function, you are squaring the entire function once. So if that function was a binomial, we would have to FOIL it. When we square 2x, we're squaring the coefficient and the variable. So this is 4x squared. So our arc length is going to be the integral from -1 to 3 of the square root of 1 plus 4x squared dx. Now this section is a really good example of what I told you at the beginning of the semester, where we're learning a lot of things here that integrals can do for us. And we're going to be setting up some integrals that we might not necessarily know how to evaluate yet. And this is one of them. We're going to learn how to evaluate the square root of 1 plus 4x squared by hand in chapter 7. But right now, you don't necessarily know how to do that. There might be a way for us to very cleverly figure it out over an hour or so. But for right now, we're not really concerned with figuring out how clever we can be and taking over an hour to do this problem. Right now, what we're concerned with is learning how to use integrals to figure out arc length. So the most important thing is understanding the arc length formula and being able to set up this integral. Now, we're just going to evaluate this integral in the calculator, which means we are not going to get an exact answer, most likely. So in the calculator, to do definite integrals, we go to our math menu and choose option 9. Now, if you've got a fairly new calculator, this is going to put the integration symbol on your home screen and really just some plug-in boxes. So it's pretty self-explanatory. You just match it up with the exact same integral you just set up on your paper. If your calculator is pretty old, all it's going to put on your home screen is the FNINT, the function integration, and a parenthesis. And the 4 things that go in those boxes, we have to type them in after the parenthesis, but we have to know what order to put them in. Otherwise, it's not going to do it. So first you type in your integrand, so the square root of 1 plus 4x squared, and then comma. And then you do your variable, which is here. We're integrating with respect to x, and then your lower bound, which is -1, and your upper bound, which is 3. And then we can hit enter, and it will give us an approximate distance. And you can compare this with the straight line distance. This is always going to be bigger than the straight line distance, so we can check that. And the picture will tell us if it's going to be a tremendous amount greater or just a little bit bigger. So I'm going to check what our calculator answer is. I got about 11.23 units in length for my arc length. And like we said just a minute ago on the graph, the straight line distance would be from -1 to 3.7, and obviously that red line is shorter. If I had to guess, I would say that the arc length is about 1.5 times longer. But let's check it and let's see. So the straight line distance. Now, it did not ask us to in the directions. I'm just curious. This is going to go from -1 to 3.7. So remember, for straight line distance, we find the difference in our x-coordinates. 3 minus -1 is 4, and we square it. And then the difference in our y-coordinates, 7 minus -1 is going to be 8, and we square it. So that's going to be 16 and 64, which is square root of 80. And so that we can compare it, we'll probably want to change that to a decimal. And I got about 8.94. And that's about 1.25 times longer. So not quite 1.5, 1.25 times longer. So your straight line distance should always be shorter. The shortest distance between 2 points is a straight line. We are doing, with arc length, we're doing curved distance. We're following a function. So let's just try one more really quickly. We're going to find the arc length. on the function. F of x equals e to the negative 2x on the interval from 0 to 4. So e to the negative 2x looks a little like that. Goes through the point 0, 1. That's where our arc is going to start. If you plug in 4, you get e to the negative 8, which is a really small number. So that's what we are calculating. Now, if you connect these 2 points with a straight line, do you think there's going to be much difference in the straight line distance and the arc length based on the picture? I don't think there's going to be much difference. Definitely, if you do both, the straight line distance is going to be smaller. It's always going to be the shortest distance, but based on the picture, my arc length shouldn't be that much bigger. All we were asked to do is find the arc length, so let's do that one first. F prime of x is going to be negative 2e to the negative 2x, and then we need that squared. So we take this whole thing and square it, which means we're going to square the coefficient. Whoops. We're going to square the coefficient. Negative 2 squared is 4. And then we multiply the exponent. One exponent raised to another exponent, you multiply them. So that's e to the negative 4x. So our arc length is going to be the integral from 0 to 4 of the square root of 1 plus 4e to the negative 4x. Again, we might be able to, after some really clever determination, figure out how to do this by hand. It will be much easier or much more obvious in the next chapter. For right now, we're just going to do it in the calculator. And if you've got the old school calculator, remember you type in, we're always going to go to Math 9. For the old school calculators, we do integrand, comma variable, comma lower bound, comma upper bound. And I am getting about 4.38 for arc length. And just because I'm curious, this doesn't look like it's going to be that much a difference. I want to know what the straight line distance is. So I labeled my points there. We've got the point 0, 1, and we've got the point 4, e to the negative 8. So remember, straight line distance, you're going to find the difference in your x coordinates. 4 minus 0 is 4, and then we square it. And then this next one I'm going to do in the calculator, we've got e to the negative 8 minus 1, and then we're going to square it. And then we add them together in square root. And I got, for the straight line distance, 4.12. So it's about a quarter of a unit off. Quarter of a unit off. So it's not that much. My arc length's just a tiny bit longer. So I'm just throwing the straight line distance in here out of curiosity. These directions are not asking us to do that. They're just asking us to find the arc length using our calculus formula. So 11.23 is what they were asking us to do here. So pretty simple. And that's all that's in this section is that arc length formula.